In this video, we're going to prove that tau of n is an odd integer if and only if n is a perfect square. I just have a feeling that you can write this proof without going forward and backwards. And if one of you viewers see that, leave in the comment section how I could get around doing the proof in both directions, that is, separately. Talking about proofs, if you like seeing mathematical proofs, then you should subscribe to my channel. This is all we do on this channel. We do mathematical proofs. Okay, so we're going to start off with, suppose that tau of n is an odd integer. We know that if there are m divisors of n that are less than the square root of n, then there are m divisors of n that are bigger, that are greater than. In the last video, I proved that these divisors of m yield, these divisors of n yield an even number of divisors. Remember, these even number of divisors, they came from divisors that are less than the square root of n, and the rest were greater than the square root of n. The only option to get one more divisor is if the square root of n divides n. That is the square root of m is m, or n is m squared. Okay, why can't you get 3 more divisors? Because there are 3 types of numbers that we're interested in. Numbers less than the square root of n, numbers bigger than the square root of n, and the square root of n itself. We have, say, m less than the square root of n. We have an equal amount bigger than the square root of n, and so far that's 2m. The only way you're going to get an odd number, that is, forget odd or even, the only way you're going to be more than 2m is if this number divides n. And coincidentally, that just adds 1. So this is odd. Okay. Now, to go the other way, I don't see much different in the proof. If n is a perfect square, suppose that n is a perfect square. So n is equal to m squared, which implies that m is the square root of n. and m divides n. Okay, m divides n because n is a multiple of m. The multiple happens to be m itself, but it does divide. Okay, so that is one divisor of n. M is one divisor. Now, suppose there are q divisors of n such that q is less than, not equal to, q is less than the square root of n. That is less than m. That implies that there exists q divisors of n such that no, I don't like the way I worded that. Having q here is interesting, such that each of the q divisors of n are all less than m. But that implies that there exists q divisors of n such that each of these q divisors are bigger than the square root of n, such that each of these divisors are greater than the square root of n, which is m. Okay, so again, you have the square root of n less than you have q divisors, greater than you have q divisors, and m itself is 1. So there are q plus 1 plus q, which is 2q plus 1 divisors for n. This is an odd number. That is, n has an odd number of divisors. And that completes this if and only if proof. Once again, if you like seeing proofs like this, you should seriously consider subscribing to my channel, because once again, that's all we do here. See you guys in the next video. Click the like button, subscribe. See you guys in the next video, and watch and learn.